Hello friends, today we will study reflection of a plane wave at normal incidence. Of a plane wave, that is actually an EM wave at normal incidence. Now, whenever an EM wave is traveling from medium 1 to medium 2, then there always be some reflection at the interface of these two media. That is, if we consider this as incident wave and this as reflected wave, then this is your incident wave. Assume that this is your incident wave and this is your reflected wave. Okay, and this is your transmitted. Now, whenever an EM wave is incident from one media to another media, then due to the difference in properties of these two medias, that is mu1 epsilon 1 and sigma 1 of medium 1 and mu2 epsilon 2 and sigma 2 of media 2. Due to these values, the incident wave will get reflected back from the interface, and part of this incident wave will transmitted to the another side, that is medium 2. Means some part of the incident wave will get reflected and some part will get transmitted to the medium 1. As you know that these three parameters are important constituent of intrinsic impedance. Okay, and whenever these three values are different for two different medias, it means their intrinsic impedance will also not be equal, and due to the inequality of intrinsic impedance of these two media, this reflection of the EM wave will occur. Okay. Now assume that EM wave is traveling in positive z direction. Okay, it means it looks like this. this is the direction of propagation, this, and we have assumed that the E is lying in the direction of X and H is in the direction of Y, so that this plane which forms at this Z is equals to 0 interface with an vector AK, which is AK is the direction of propagation of this EM wave, okay, is normal to the interface of the two medias. If this is your medium 1 and this is your medium 2, then this arrow, that is this vector, will have an angle 90 degree with this interface of the two media, that is like this. Okay, this form a 90-degree angle at this interface, at this interface. Now if we again look it in another way, that that this part, that is this part, is drawn in a 3D way, and if we convert it in 2D way, then this must be like this, that is this is your direction of propagation and this is your direction of E, that is electric field E, and H is in the direction of Y, which comes out of the screen. So this can be represented like this with a dot here. Okay, so this will be your H. Now assume that this incident wave is denoted by EI and HI, so that this will be your AI, where AI is the propagation vector. Okay, now if this will get reflected back from this surface, then what will happen, that is at the interface, at this interface, the reflected wave will have opposite direction with the respect to this incident wave, that is it will be like this, like this. Okay, it means here the direction of E will remain same, but the direction of propagation is changed, of the reflected wave is changed. So this is your reflected wave, so the direction of H will also get changed, and this now becomes HR, and this will be in the direction of minus Y. Okay, now it means your medium 1 consists two waves. One is the incident wave and the another is reflected wave, where this is z is equals to 0, and some part of the incident wave will be transmitted in medium 2. This is your transmitted wave. So this is your transmitted wave. Transmitted wave have the same direction. So in this way you can say that transmitted wave has E in the same direction with transmitted AT in the same direction Z, that is Z, and H is in the same direction, that is Y. This is your transmitted wave. Okay. Now again consider the incident wave first. So we have assumed that incident wave is denoted by EI and HI, and suppress after suppressing e raised to power j omega factor, we will get only EIS, which is a function of Z. Okay, that is only the phasor part will be contained in this case, and assume that it has maximum amplitude denoted by EI naught e raised to power minus gamma 1 Z AX, where gamma 1 is the propagation constant of medium 1. Okay, that can be denoted by alpha 1 plus j times beta 1. Okay, where alpha is the attenuation constant and beta is a phase constant. So this is an important part, incident wave. Now similarly we can also have HIS Z is equals to, let us suppose the maximum amplitude of H is magnetic field intensity, H is HI, where HI stands for incident, okay, and e raised to power minus alpha Z AY, and if we write this in terms of eta and EI naught, then we can say that this will be equal to EI naught divided by eta 1 e raised to power minus alpha 1 Z AY. Okay, like this. So there are two important parts. Incident wave consists E and H both. Now consider the reflected wave. Now in case of reflected wave, we have assumed that the reflected wave is denoted by ER and HR with the same condition that we have suppressed here in this case. E raised to power j omega factor, that is e raised to power j omega factor is suppressed here. Okay, so ERS phasor part of reflected E will be in the direction of Z, but here the direction, sorry, it's a function of Z, okay, with a direction in minus Z direction. So assume that it has maximum amplitude ER naught e raised to power, because the direction is changed, so this will be positive here, Z A X. Okay, so this is another equation. Now for HR it will be like this, HR naught e raised to power gamma 1 z, but the direction is now changed, so this will be minus ay. We can also write this minus sign outside by taking minus sign outside. HR naught e raised to power gamma 1 z ay. If we replace it in terms of e, then minus e r naught divided by eta 1 e raised to power gamma 1 z a y. Okay, these are very important equations, so close them in the box. Now consider the transmitted wave. Here the transmitted wave is denoted by E T and H T, so that E T S, where S stands for phasor, is a function of Z, is equal to E T naught e raised to power gamma 1 minus gamma 1 z a x, okay, and h t s z will be equals to h t naught e raised to power minus gamma 1 z a y equals to e t naught divided by eta 2, because this transmitted wave exists in medium 2. So, oh sorry, this must be gamma 2 here, this must be gamma 2 here, because the wave is present in transmitted wave is present in medium 2, so these two factors will be gamma 2 and gamma 2. So this will be e raised to power minus gamma 2 z a y. Okay, now applying the boundary conditions, at z is equals to 0, that is, we have assumed that here in this case, that is, this side is positive z and this side is negative z, and this at this interface this will be actually z is equals to 0. So We have to apply the boundary conditions at this point, at this interface. So, and we know that E has only the tangential component. So it consists only the tangential component. So E tangential 1, that is E1 tangential, is equal to E2 tangential, and similarly H1 tangential will be equals to H2 tangential. Now, if we look at this medium 1, then medium 1 consists two waves, incident wave and reflected wave. So we can write the complete E in medium 1 that E1 consists of E incident plus E reflected, and H1 will be equals to H incident plus H reflected, and at Z is equals to 0 we will get this condition, that is this. Okay, we will get this condition. Leave it, that is this condition. Okay, so due to this condition, at the interface we will have E I naught, because Z becomes 0, plus E R naught is equals to E T naught. And at this condition, the transmitted wave will be equal to the total wave present in medium 1 will be equal to the total wave present in the medium 2. And this will be equal to, because at if we put Z is equals to 0 in this equation, that is this one, then this becomes 1. So we will left behind only the maximum amplitude. So we will get here E I naught plus E R naught is equals to E T naught, and this will be your, let us suppose, equation number 1. Okay, similarly we can have H I naught plus H R naught equals to H T naught, and this will be equals to, if we put its values, then E I naught divided by eta 1, because maximum amplitude of HI naught is this part, minus, because it consists a minus sign here in above equation, you can see from there, that is eta 1 equals to Et naught divided by eta 2. Okay, assume that this is equation number 2. Solving equation 1 and 2 for E R naught and E T naught, we will get that E R naught will be equals to eta 2 minus eta 1 divided by eta 2 plus eta 1 and multiply times, that is EI, and will be equal to R. This vector is denoted by R. Actually, this is reflection coefficient EI naught. Okay, where R is equals to reflection coefficient that is ER naught divided by EI naught is equals to eta 2 minus eta 1 divided by eta 2 plus eta 1 is actually reflection coefficient. Okay, so, and if we again resolve it for Et naught, then we will get second term. This is your first term. Second term, that is Et naught is equals to 2 times eta 2 divided by eta 2 plus eta 1 EI naught, and if we replace this by tau EI naught, then we will get this relation. Okay, where tau is actually E transmitted divided by E incident, and this will be given by 2 eta 2 divided by eta 2 plus eta 1, and this is actually your transmission coefficient. Okay, so again take a look at these two quantities, that is reflection coefficient and the transmission coefficient. This is your transmission coefficient equation. Okay, this is your transmission coefficient equation. Look at this quantity, that is this one. This quantity is actually a ratio and it is always unitless. Okay, so we will get a point here that tau, sorry, R is unitless. Another point you can find out that as eta is a complex quantity, you know it very well that because eta in general is equals to under root j omega mu divided by sigma plus j omega epsilon, which is a complex quantity. This may be real also depending on this factor. So R may be real or complex. It may be complex also. Similarly, in this case, in the case of tau, that is transmission coefficient, that tau is also unitless and it is also a complex quantity. Okay. Now again look at this factor, that is this is a ratio of n to eta 2 minus eta 1 divided by eta 2 plus eta 1. It means this quantity will always be less than 1. This may be positive or this may be negative depending on these two factors. Okay. Then third important point to be noted is that the range of reflection coefficient will always be 0 to 1. Okay. Now if we add one in this quantity, what will we get? Look at, that is eta 2 minus eta 1 plus eta 2 plus eta 1 divided by eta 2 plus eta 1, and these two get cancelled, so we will get 2 eta 2 divided by eta 2 plus eta 1, and this is nothing but it is actually tau. So we can say that there is a relation here, that is 1 plus tau, sorry, 1 plus reflection coefficient R is equals to tau. So please note these formulas, these are very important here. Okay. I am highlighting the important part here. This part is very important. This must you know about it. This is unitless. Okay, these two formulas are very important. This one and okay. Thanks for watching this video.